Okay, so substantially, I will talk about wood, trees, I mean wood actually, as a construction material, and its basically complexity and well, what we learn from it. Okay, so I guess we can all agree that trees and therefore wood, since it's also an organism, it's actually complex, although this is not quite the way people perceive it, at least not in industry. So the fact that they call it a material already sort of goes against that principle, because a material, well, it's something that's completely opposite of complex systems, no? So in any case, well, it satisfies, sorry, I can't see. So it satisfies most of the, well, I mean, it's also a problem of what is complexity, you know, so I won't go into that right now, but I guess there are many definitions, but I guess, yeah. So I've added some here that you can read. And this is basically what a tree looks like, okay? So I've shown, well, not me, but this is a very nice image, actually, that represents the full evolution, know how the tree starts from a molecular, let's say, nanoscopic or microscopic scale, and how then it goes through all these stages where you actually, you know, present itself as a tree, you know, what we actually see on the macroscopic level. So the let's say the astonishing thing, at least for me, is that trees are made of just 3 elements. You know? So there's cellulose, hemicellulose, which are macromolecules substantially, and lignin, which is something like a crystal. And these two sort of macromolecules are held together with the lignin. So you can imagine like spaghetti, and then you put cement on top and makes it sort of structure that is quite strong, resistant. It has very nice properties, and that's why we use it for construction. So it's it has very strong tensile strength, tensile strength, and it's light, so it's porous and hierarchical. So perfect for us, at least for me. Anyway, so what is the scope, at least, of the things that I'm doing? So, well, we got a lot of, no, so the thing is that, well, at least in Switzerland, the wood industry is very big. So they get a lot of resources from there. And the plan is now, because of all this talk about climate change and the need to move away from cement, which causes a lot of carbon dioxide. So they're now thinking of exploiting wood for building, let's say, huge constructions. You know? So I'm not talking about small houses or bungalows, but rather 15-story buildings and so on. So there's going to be a need for a lot of it. Okay, so, and well, we have limited resources. So the first step would be to optimize somehow the use. And in order to optimize, we have to understand wood a bit better. So since it's a living organism, it's very heterogeneous, and therefore its mechanical properties, which are very important for the industry, are also themselves very heterogeneous. What this means is that you can have the same tree in the same forests, you cut 2 pieces, which are maybe 1 meter long, and they will have completely different mechanical properties. And this is very bad news for architects and so on, because when they build a building, they want to make sure that it can hold a roof and so on. And a very, let's say, popular product from these type of, let's say, boards are things called glue lams. So they are basically lamina, so wood that are glued together, or cross-laminated timber, which are actually panels, huge, that they use, and they basically use them as walls, no, on these big buildings. Okay, so we have from industry, we got something like 1.5 million samples of wood properties. So what they do is they have these big machines that are very costly, and most of them are made from one company called Microtech, which is actually, I think, in Trento. And they have these big scanners you put inside these boards. After you saw them, you cut them. So you get this big log, you cut it into pieces, into lamella, and these lamella go into the scanner. And the scanner basically takes x-rays and other stuff, pictures and so on. It also applies pressure, so it calculates the modulus of elasticity and the modulus of rupture, the density, moisture, and many other things, okay? And from there, they can then conclude let's say, they grade the wood, basically. So they give it a grade, which is based on the tensile strength. And all this is, of course, inferred, no? Because the only way that you can know, like if you get a sample, the only way that you can know what the strength is to actually break it, no? But you don't do that because you need it. So what they do is they make these models, which have been done like maybe 50 years ago, and they're statistical models using regression, and they're usually linear. So all this is very old. And the thing is that the industry is very slow to change because they have a lot of standards and so on to follow because of safety and, you know, so yeah. So what we are trying to do is to make a new model, a new system for grading wood, okay? So I want to have, if you give me a sample of wood, I want to tell you how many newtons it has of bending strength, for example, and also for how much pressure you can apply before it breaks. So to do that, we based, let's say, so we wanted it to make it non-invasive and fast and so on. And the best thing for this is images, okay? And I will come to it right now. The only problem is that it's beyond me why they have like 1.5 million samples and they only gave us 15,000 images, but I don't ask questions, I just solve the problem. So this is a problem actually because it's too small, the sample. But anyway, so I'll come to that soon. So so the idea is this, that so we get something, well, this is a bit cherry picked. No, actually I got this from the internet. This is not actually the data, but just for you to understand. I mean, so this is a sample, and also you can see that it has all these fiber directions, you know, and this is sort of a fingerprint because no two samples will be the same. And so the idea is then this, well, okay, if there must be some information encoded into like these patterns that can tell us something about the strength. And this is not just like naive thinking or a guess. Actually, most of the time, this is, I mean, they don't use actually the lines, but what they do is they check, for example, for knots, because these are the weak points, you know, of a structure. So if you bend a piece of wood, it will usually break at a knot. So if it has a lot of knots, the quality will be very low. But then we thought, okay, well, if knots are also somehow a discriminant, maybe, you know, even these patterns could be that. And why? I mean, logically thinking, this is what it looks like. So what I showed you before. So this is basically the sample that we have. This is a macroscopic structure. If you zoom in, so this black box, it becomes like this, and then, you know, so on. And finally, it comes down. Also, this is the same thing. So these two are the same. So you have these cell walls, which are very important. And actually, these cell walls are, at least in, let's say, spruce, so Christmas trees and so on, in pine, you know, in conifers, softwood. So these maybe you can identify with this because it's these cells, their size changes during the seasons, and this is what gives you the rings, you know, because they get denser. So the diameter of the cell gets smaller and smaller because there's not so many nutrients during winter. And then when you get spring, they get bigger. And that's how you actually see the rings, and that's how you get these patterns, okay? So, and going on, I mean, this is what creates the strength from a microscopic scale to the macroscopic, okay? So it makes sense to look for the information inside here. And how to do that? I mean, the best thing is now we have machine learning, so without wasting any time, you know, we took these samples. So these are the actual samples we got from the factory, from the sawmill. So so we have, this is the input, the image, and the output is the, so here we use actually only 3 inputs out of many. So we have the modulus of elasticity, so the static and dynamic one, and the modulus of rupture. So these are actually the indicators that they use themselves for grading wood, okay, giving it a grade, quality grade. So there were a lot of things to do. This took a very long time. I mean, it's not like just worked out of the box. We had to do a lot of things. Here I just present the, let's say, final stage. So we have an image that goes inside, and also we have to train it with many. We have like 15,000 images. They all go inside, and this is the label, okay? And the model itself has a augmentation, let's say, layer. There's a feature extraction layer, and then a regression layer. So what we do is we augment the model because we only have 15,000 pictures, images, which is not enough, like especially for, we used deep learning, so 15,000 is not really a big number. Especially here, I mean, I want to stress that we are doing regression and not classification, which is much, much more difficult. And Anyway, and we have like a vector of 3 points to predict, basically. So what we did was we used a deep neural network. So for those who've never seen it, heard it, but never were too afraid to ask what it means. So simply stated, a deep neural network is something like this, where you have an input layer, an output layer. So for us, it's an image like here. And well, here the output is like the category. So this is classification, actually. So, you know, you have, what are these, like 4 classes. For us, actually, it's a number. It's a real number. So that's why it's more complicated. Anyway, so what you do is you have a lot of pictures. So here, in this case, it's Washington. So they probably have a lot of different presidents or, yeah, anyway, that go first into the model. No, so they present it to the model. The model sort of reacts through, let's say, mathematical operations in all these nodes, okay, and goes through these layers, and then comes the output. And something at the beginning, of course, when it's not when it's initialized to like random, it will randomly also give an answer here. So what you have to do is, this is called supervised learning. So you have to tell the network, look, if you gave something that's not George Washington, you have to say, no, no, this is not good. You punish it. So you punish the network with a signal that goes backwards and corrects a bit these weights, and so on. No, but if you get the correct answer, then you reward it, and that's how it works. That's very, say, the basics. Okay, and each layer produces. You see what is shown here is very nice. So here, for example, it might identify only edges or like parallel or vertical lines. And the representations get more complex as you go, you know, along the depth of the network. And something that came out recently, well, it's not recent anymore, are these residual networks. So what happens there is that you have a deep network, but then there are also these shortcuts. Okay, so that's the only difference. I won't go too much into detail here. And that's a residual block. So you have these 2 normal layers, and then let's say the next layer will be fed in what comes out, f of x, plus what came in from x. Okay, so like, and this proved to be very successful, and like everybody's using this now. So if you're doing this, let's say, beats all the contests in image recognition. Okay, so coming back, so we used basically a residual network, but pre-trained. Okay, so we didn't want to start from like inventing the wheel. So we actually just downloaded a model which is pre-trained on something like, well, I wrote it here, I think. Oh, sorry, what happened? Anyway, it was pre-trained on millions of images in 20,000 categories. There it is. So 14 million whatever images, no, and 20,000 categories. So we used that, okay? And we did 2 things. So we used the, let's say, the model the way it is, okay? So we froze all those weights. So all these connections that you see here, we just froze them from the pre-trained model. So we didn't touch it. What we only did was we added this regression layer and played with that just to see what this model could do, you know, without ever seeing samples like this before, okay? And then after that, we relaxed this condition. So we unfroze the layers, and we basically additionally to what was trained before on these like 14 million images, which were images of cars, you know, the normal stuff you see everyday life. So we presented then something, you know, like this, which it has never seen probably before. I doubt that they trained it on wooden boards. And I will now show you the results on that. But keep this in mind, okay? So we have, there are 2 sort of layouts, okay? One is where the pre-trained model is sort of the way it was before, and the other one is where we actually retrained it further with our data also, okay? And also what is important to sort of, sorry. Yeah, so that's called fine-tuning, sorry. So the fact that, you know, you unfreeze these weights and you train further, that's called fine-tuning. Makes sense, no? Okay, so we have the augmentation, yeah, and here also I wrote it's actually feature extraction. So what we do is we use this pre-trained deep learning network to extract features. So because what goes in is a multi-dimensional image, you know, that's very big. So this basically acts as a, let's say, encoder somehow. Okay, so it encodes all the information that's inside here into an array. you know, once it comes out of the green box, we get an array of 2024, an array of numbers, okay? And then these numbers go into the regressor. And then from the regressor, we try and predict what these values will be. So what we did was, so here's the regressor. We tried different regressors, okay? So we froze basically the weights, and that's indicated here where it's written without feature, okay, fine tuning. So for example, there's a regressor called Elastic Net, and then it works quite well, actually. You can see that it gets to 0.9 above, no, for the R² value, which sort of in normal parlance would say that it can explain 90% of the variation, okay? So which is very good, actually, at least for us. So these are the different types of regressors, and when we switch on the feature, the fine tuning, you see the results are much better, but they're not bad either without, you see, so you have almost 80% in this case, and here also. So out of the box, it works quite well, and then with fine tuning, it works better, of course. And I imagine that if we had a bigger set of samples, which is possible because there are, I mean, they get like something like 2,000 per day in a single sawmill, no, images. So you can just imagine how many you can get every year. Okay, so this is the result basically that I was aiming for, okay? And here, what I can show you are different models that we used. So these two here are the ResNet model, this big model that I explained. And just to make sure that we were doing things correctly, we also used a small model, which was only with 5 layers, just a simple convolutional neural network. And even there, the results were quite good, as you can see. So we get something like 80%, no? And this is without augmentation and with augmentation. So if you use this model ResNet with augmented data, and by augmentation, I mean that you rotate some images, you put some noise inside, you change the contrast and so on. There are tricks to do that. So we were very happy. I mean, I guess the industry even happier, because usually what they do in machine learning is that they try to compare it to something already known. But the problem is that if you give a human a board, you know, to inspect, I mean, there's no way they even get close to this, okay? So for the industry, I mean, this is already, I mean, for them, even 60% would have been okay, but 90 is much more than they expected. So, sorry, 2 minutes, okay. So I was able to satisfy my employers, okay? But then I did something, let's say, for me. So I tried then to put this into context of complexity. So since it's complex, I tried somehow to put it into context of complexity. And since we have a hierarchical system, you know, that starts from very small elements, the molecules, then goes higher and higher, like, how can we describe it? And also what's going on inside? So obviously there's some type of emergence happening, okay? And now the good question is, what is emergence? Because I don't know, at least you can help me, but I've never found any like clear definition what it means. Until I came across this paper here by Tononi, and here actually they try to even quantify it. So I tried to put this, the results that we had, into the context of the theory that Tononi himself developed. I think it's him, at least that's what he says. So they came up with this effective information, which is a general measure of causation. So for them, causation is important for emergence. I mean, it sounds like simple-minded, but unless you go through all the mathematics and you actually derive something like this Kullback-Leibler divergence, and also they used basically to define the. I mean, the effective information is a function of the Kullback-Leibler divergence. What they sort of came up with is that the macroscopic level with the highest effective information gives the best mechanical prediction of wood. So what does this mean? This means that there are many levels. So this might be microscopic, but the rest are all macroscopic. And so from the small, let's say, experiments that we did, I can say that so you see the blue line here, which is continuous, and then the broken one. So the blue one I can prove, because if I reduce the resolution of the image, which means that I'm coarse graining it, I see from the results that I get on my computer that the prediction gets worse. I mean, this could be obvious, but to actually show it in the context of this whole model, I think it's beautiful, no? And why it works so well is that we basically have a natural system that is hierarchical. So it's easy to somehow, once you start coarse graining, you know, so if you start from here and you start coarse graining, you're basically measuring. I mean, if this were only like a system that was completely predictable, like a simple formula from which, if you know the initial condition and the boundary condition, and then you can calculate it forever, then there will be no new information coming, you know. But since here, apparently, we get more and more information, because what happens is that these elements, you know, at different coarse-grained levels, they interact, you know. And this is what creates more information. This is what creates diversity, and this is what creates heterogeneity. And it's only until we reach this level where we can stop, because going beyond in the context of this example, no, because what I'm trying to find out is the strength, will not make sense anymore, because if I know what the tree looks like, it will give me no information about the strength. So, well, anyway, sorry to keep you waiting, but I'm just trying to explain this to myself also, because I think this is a nice way to, because it's not just wood, no, so there is many other stuff. Wait, what happened now? It's a big, yeah. So as you can see, we have muscles, we have bamboo, we have bones, we have tendons, and so on, which are all hierarchical, and they can, I think, all be placed in this same context of the theory of Tononi and of information, and how it's propagated from one level to the other. And yeah, that's it. I would like to thank you all. Sorry for taking more time. I don't know what else. I wanted to thank my co-workers. So I did this thanks to a grant from the Swiss Federal Office for the Environment, and I did it with some students from DTH, and especially, I mean, they did all, let's say, a lot of the heavy lifting, and especially Laura. So she just started her PhD. So you should look out for her. It's the next star in biophysics and bioinformation. All the others deluded me because they left. They went to industry. And my boss, Mark Schubert, so who works with me in the wood tech group. Thank you very much. Sorry.